All right, so this is Chapter 5, Section 8, Exponential Growth and Decay Models, Newton's Law, Logistic Growth and Decay Models. So this is the why we do what we do, all of this Chapter 5 stuff. Our first learning objective is to find equations of populations that obey the law of uninhibited growth. So uninhibited growth formula, so make sure, highlight this little guy. Girl. So A of t equals A sub 0 e to the kt. And true or false, this is, we did this equation, or we've seen this before? Seen this equation before? Okay. So when k is greater than 0, we have growth. When k is less than 0, we have decay. So this is uninhibited growth of cells, like, you know, how bacteria grows. We've all seen those movies. A model that gives the number n of cells in a culture after a time t has passed in the early stages of growth is n of t equals n sub 0 e to the kt. Boy, this looks a lot like the growth formula. When k is greater than 0, where n sub 0 is the initial number of cells, k is a positive constant that represents the growth rate of cells. All right, example problem, bacteria growth. A colony of bacteria struggling for freedom and rights grows according to the law of uninhibited growth. Just kidding, colony. To the function n of t equals 90 e to the 0.05 t, where n is measured in grams and t is measured in days. Determine the initial amount of bacteria. We can tell that just by looking at it, right? What is the growth rate? What is the population after 5 days? How long will it take the population to reach 140 cells? And what is the doubling time for the population? The really kind of an important thing that will keep coming back up for us is questions that are phrased like E. So while A through D are important, E should be our laser beam focus. All right, so when we plug in 0, it knocks this whole exponent to 0, and anything to the 0 power is 1, and it leaves us with just the 90 as our initial amount of bacteria, 90 cells. Our growth rate of bacteria is 0.05, which, remember, if they want it as a percentage, move the decimal place to the right 2 places, and you get your percentage as 5%. The population after 5 days, so we plug 5 into the formula. 0.05 times 5, raise it to the e power, times it by 90, and round it to the nearest cell. You get 116 cells. Make sure you know how to do this on your calculator. If you don't use the right amount of parentheses on your exponent, you will not get the correct answer. So just double check these guys with the ones you know the answer to make sure you're doing your operations correctly. So D, how long will it take for the population to reach 140 cells? So we set it equal to 140. Then we divide by 90. And then we take the natural log of both sides because the opposite of base E is the natural log. And 140 divided by 90 reduces to 14 over 9. Natural log of E to the 0.05t is just 0.05t. We divide by 0.05. Chug that into our calculator. Once again, practice putting this into your calculator to make sure you can get the right answer out. All right. Now the important one, E. So E says, what is the doubling time for the population? If we initially start with 90, to double that would be 180. So that's where that 180 comes from. Then we are going to divide by 90. And lo and behold, 180 divided by 90 is 2. Then we're going to take the natural log of both sides. So natural log of 2 equals, natural log will eliminate the base e, so I'm left with just my exponent. So natural log of 2 equals 0.05t. Then I'm going to divide by 0.05. And it will be approximately 13.9 days. All right. Colony of bacteria increases according to the law of uninhibited growth. If n is the number of cells and t is the number of time in hours, express n as a function of t. And then now we're going to use the other numbers to put together a better equation. If the number of bacteria doubles in 2 hours, find the function that gives the number of cells in the culture. How long will it take for the size of the colony to triple? How long will it take for the population to double a second time? That is increased 4 times. If you look, nowhere in this problem do we have an initial amount of bacteria or any amount of bacteria. We just have time increments. So let's see how we deal with situations where we have no bacteria time. So let's take our initial equation, n of t equals n sub 0 e to the kt. B says we are going to double in 2 hours. So whatever our initial value is, we're going to have twice that amount in 2 hours. So what's going to happen to this n0 when I divide both sides by n0? N sub 0 divided by n sub 0 is equal to
0 or 1.
1. Right, n sub 0 times n sub 0 is equal to 1. 2 times 1 is 2. And then I have e to the k 2. So in this situation, what gets rid of our base e is a natural log. We take the natural log of both sides. So we didn't even need the amount of bacteria in order to find that constant. I divide by 2. And I get our k is approximately equal to 0.3465736. Yay. So now we can put this equation together. If you have to input it in for either the practice or the quiz, it will tell you what to round it to. Or to leave it as exact. All right, C. We're going to do the same thing, but now it's going to triple. So we have n sub 0, n3, n sub 0. We're solving for t. Our k is the value we calculated in B. So we get, when we divide by n sub 0, we get 3 equals e to the 0.34 t with the natural log of both sides, and divide by our k, and we get approximately 3.2 hours. And then, how long will it take for the population to double a second time? So if the population doubles in 2 hours, it will double a second time in 2 more hours for a total time of 4 hours. It's going to continue the same rate. Promise. Okay. Second learning objective, find equations of populations that obey the law of decay. So we were population growing. Now our poor little swamp monsters are going to be decaying and creating fossil fuels that we can drive around in our car. Just kidding. The amount A of a radioactive material present at time t is given by, oh, this formula looks familiar, except now K is less than 0. So K is a negative number, and that's going to represent our rate of decay. All right, traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,600 years, approximately when was the tree cut and burned? Ooh, so real life, Indiana Jones archaeological dig. So we're talking half-life. So we know that half of the carbon is left over after 5,600 years. We are trying to find the K value. So once again, we're going to divide by A sub 0, divided by A sub 0. And we get 1/2 equals e to the 5600K. Take the natural log of both sides. Are you guys feeling the process? There's a rhythm to how to solve these, and it's the same every time. And then divide by 5600. So we see when we do natural log of 1/2, and remember, natural log, when you're graphing it, comes up from negative infinity as it gets closer to x equals 0. Comes up, comes up, comes up. It's negative, negative, negative. Hits the x-axis at 1. And so when you're trying to take a natural log of 1/2, it's going to be a negative number. It's negative 0.000124. Okay, so that gives us the K. Now we're going to put the equation together. If we have 0.0167, if we have 1.67% left, so we're going to take our initial amount and times it by that percentage we have left. We divide out the A sub zeros. We take the natural log of both sides. We divide by our K, negative 0.000124. And we get approximately 33,000 years ago, that tree was cut down and burned. And that's how we carbon date stuff. All right. Newton's law of cooling. Oh, man. Love science. This is great, guys. So, here's the formula for Newton's law of cooling. Temperature U of a heated object at a given time t can be modeled by the following function. U of t, so this is the temperature U, equals t plus U sub 0 minus t times e to the kt, where k is less than 0. If we're cooling, we want our temperature to decrease, so that's why this is in the decay part. Where T is the constant temperature of the surrounding medium. U sub 0 is the initial temperature, and K is a negative constant. All right, Newton's law of cooling. So let's see how to use that. A cake is heated to 350 degrees Fahrenheit and is then allowed to cool in a room whose air temperature is 70 degrees Fahrenheit. If the temperature of the cake is 300 degrees Fahrenheit after 5 minutes, when will its temperature be 200 degrees Fahrenheit? All right, so let's put together an equation. So our formula U of T, our temperature of our surrounding room is 70. Our temperature of our cake when it first comes out of the oven is 350. So remember, we're solving for the K. A is, when will its temperature be 200? Boom. So we know that after 5 minutes, the cake is 300 degrees Fahrenheit. Okay, so we're going to use, we know that after 5 minutes, 300 degrees Fahrenheit, so we're going to plug that into our formula and chug out the K so we can get the constant. So think about order of operations. I got parentheses here, so can I get rid of the 70 pretty easy? Yeah, let's subtract that from both sides. And we can combine 350 minus 70 is 280. Then let's go ahead and subtract out that 70. Gives us 230. Divide by 280. Guess what happens next, guys, in our solving? We've done this 4 times already today. When we get to the part where we have just e and an exponent on one side and the other one on the other. Yeah, Josh got it. Natural log of both sides. So when you get to here, this is where, if I'm not thinking, I'm just going, doing my algebra. If I get here, this is the new stuff. Oh, just kick it into gear. I take the natural log. Natural log will get rid of a base e. Then we divide by 5. Chug away in our calculator. Our constant is 0.039342. So let's march that back. Chug that into our equation. So it appears here. And when will its temperature be 200? So we're going to set this part equal to 200. Subtract out 70 to get 130. Divide by the 280. It's Jennifer's turn. When we get to the E, natural log of both sides, yeah. Then divide by our constant, and we get approximately 19.5 minutes. Please tell Kelly that we learned this. It was all cool. It's all physics awesomeness. Okay. Determine the elapsed time before the temperature of the cake is 100. So we're going to set this equation again equal to 100. Do the same process. Subtract the 70 to get 30. Divide by 280. Take the natural log of both sides. Divide by the constant. 56.8 minutes. What do we notice about the temperature as the time passes? We see T increases the exponential e to the negative 0.039342t approaches 0. So the temperature of the cake approaches the room temperature. Does that make sense? That if you set a cake out for long enough, it's going to get closer and closer to whatever the room temperature is. Yeah. So when you experience a cooling formula, again, if you need to highlight or whatever, or make note, as time increases, you're going to get closer and closer to whatever the medium temperature is. Not medium as like between high and low, but medium as whatever your room or area is. All right, logistic models. In a logistic model, the population P after time t is given by the function P of t equals C over 1 plus A e to the negative bt. Highlight this formula or circle it or put a star on it. Where A, B, and C are constants, A is greater than 0, C is greater than 0. The model is growth if B is greater than 0. It's decay if B is less than 0. Logistic model for a population. So the same rules apply. If we're growing, B is greater than 0. If we're decaying, B is less than 0. Do we have populations that decay? Is that a thing? Yeah. The population of Germany was not increasing, it was decreasing, so they opened immigration to increase their population since it wasn't happening naturally. Population decay does happen, not only with humans, but in a species as well. When you have an animal going extinct, I saw a video on sea otters. Sea otter population went from 20,000 to 2,000. That's a population decay. All right. So if we look at the graph, y equals whatever our c value is a horizontal asymptote, and y equals 0, or sorry, p, since it's not y anymore, it's p. There's also a horizontal asymptote here. It's going to look like a Kind of looks like a sideways cubic. It's going to go through 0, comma, p sub 0. It's going to have an inflection point at 1/2 c. So if you have to circle and highlight these little pieces of information, because I'm sure there'll be questions asked. When we have a decay, so this is for our growth. When we have a decay, it is just the opposite p-value. Inflection point still at the same place, asymptote still at the same place. Okay, let's read through these properties of the logistic growth function. The domain is a set of all real numbers. The range is the interval from 0 to c. And notice that neither of these are included because those are actually the asymptotes. Where c is the carrying capacity. And I would put a little circle or a highlight on this because this is the first time c has been defined as a carrying capacity. There are no x-intercepts. The y-intercept is p of 0. There are 2 horizontal asymptotes, y equals 0 and y equals c. P of t is an increasing function if I have growth, and a decreasing function if I have a decay. There is an inflection point where P of t equals 1/2 of the carrying capacity, that's 1/2 c. The inflection point is the point on the graph where the graph changes from being curved upward to curved downward for growth functions, and the point where the graph changes from being curved downward to curved upward for decay functions. The graph is smooth and continuous with no corners or gaps. All right, let's see. Example, our little friend, the fruit fly. Fruit flies are placed in a half-pint milk bottle with a banana and yeast plants. Suppose that the fruit fly population after t days is given by P of t equals 230 over 1 plus 56.5 e to the negative 0.37 t. State the carrying capacity and the growth. Determine the initial population. What is the population after 5 days? So as t approaches infinity, e to the negative t approaches 0. So this approaches 0. Leaving us 0 times 56.5 is 0. And then we have 230 over 1. So P of t approaches 230, which is the carrying capacity. The growth rate is the absolute value of our B. So it's 37%. Just move that little decimal over. Determine the initial population. So just real quick here. This says negative 0.37. Why am I growing if this says negative 0.37? Isn't decay negative and growth positive for that B value? Okay, so if we look at the original formula, this is e to the negative b, and it is, our real b is opposite of what appears here in the formula. So anyway, our growth rate is 37%. The initial population is when I plug in 0. E to the 0 is 1. 56.5 times 1 plus 1 is 57.5. 230 minus 57.5 is 4. So initially there are 4 fruit flies. That's a respectable amount. What is the population after 5 days? So we plug in 5 to our formula, shove that into our calculator, and we have about 23 fruit flies. How long does it take for the population to reach 180? So we're going to set this equal to 180. There are a couple different ways we can solve for this. I would probably put 180 over 1 and cross multiply. That would be my initial. Or you can multiply both sides by this denominator. then divide by 180, then minus 1 from both sides, then divide by 56.5, and then take the natural log, and divide by negative 0.37, and we get 14.4 days. Good job, you guys. Look how advanced our mathematics are right here. Pretty big deal to be this far into your math. Use a graphing tool to determine how long it takes for the population to reach 1/2 of the carrying capacity. If the carrying capacity is, we determined it was 230, half of 230 is 115. So you graph y equals 115, and you graph your function and find where they cross. So at about 10.9 days, we are at half of our carrying capacity. What effect does the growth rate B have on the logistic growth function? So if I have negative 0.03 and negative 0.08, negative 0.08 has a steeper curve. Awesome. Okay, let me see. The FSM wood product model classifies wood products according to their lifespan. There are 4 classifications: short, medium long, and long. Based on data obtained from the European Forest Institute, the percentage of remaining wood products after T years for wood products with long lifespans, such as those used in building industry, is given by this formula here. What is the decay rate? It is going to be 0.0581. Move the decimal over 2 places to get 5.81%. What is the percentage of remaining wood products after 10 years? Plug in 10, shug it in your calculator, you get 95.0. So 95% will remain after 10 years. How long does it take for the percent of remaining wood products to reach 50%? So we're going to set this equal to 50. Times both sides by the denominator. Divide by 50. Subtract 1. Divide by 0.316. Take the natural log of both sides and divide that by 0.0581. We find that it's 59.6 years. Half of it will be remaining. Explain why the numerator given in the model is reasonable. The numerator of 100.3952 is reasonable because the maximum percentage of wood products remaining that is possible is 100%. So this is around 100. Phew, we made it. Good job, guys.